Welcome to lecture number 5. Today we deal basically with this baby photograph of the universe, which I was last week already mentioning. So you see this here, these freckles, which is basically in the microwave region. And it tells us how old is our universe. I'm absolutely surprised to what narrow error margin it tells us this. But you also see already one of these problems. If we want to look back to this very old light, which is obviously very distant and traveled a long, long time to come to us, we see all the stuff before. All the stars that are meanwhile and galaxies and whatever. And here you see in this picture, you see here this bright band. This is of course the Milky Way, which we use then as a equator. And we need to peel this away, this foreground. Usually we have problems with the background. Here we have no problems with the foreground. And at first I wanted to remind you, microwaves, well, we see them usually, we have them in the kitchen, where they make our water molecules rotate in the food. And since movement of particles is also associated with the temperature, they heat up. The more the water molecules spin and hit other molecules and warm them, make them move, we heat their food up. Okay, but here now, microwaves, we will talk about microwaves with wavelengths that have 10 to the minus 2 meters, 10 to the minus 2 meters, centimeters, down millimeter, and the region going towards the infrared. Infrared, and then we pass through, we come to shorter wavelengths, and then we are at the visible. So this 400 to 700 nanometers. Wow. This is then what we usually deal with. Here infrared, remember, if you to check your house, how good it's isolated, you would take an infrared picture. Color this into blue or hot, where a lot of energy, where it's relatively warm, it means a lot of heat can make it through the walls, or better, usually the windows or the roof. This is of course where you need to work on the insulation. So to give you a feeling, just before the radio waves, we are on the microwave region. Relatively long wavelengths. So then I wanted to remind you this black body stuff. So every body with a given temperature T emits this characteristic radiation. So, and the shape is always the same. It's just adjusted to the temperature of the body. And so the shape is the same. The maximum is adjusted, and then what also adjusts to this temperature is the area underneath the curve. But essentially with the maximum, we can associate the temperature of a body. So we measure the light that comes out, all the frequencies or wavelengths, plot 4 given wavelengths, how much did we get, the intensity, plot this for the next wavelength, plot the next, and we will get this type of curve. This will be always the same. So this Planck spectra, despite these spectra were known well before Planck explained the shape with this new theory of quantum mechanics. Back then, you see here the problem of classical theory, that is called, if basically goes to infinity, we don't have this bent down, and it's called the ultraviolet catastrophe. So this was classical theory, classical physics before quantum mechanics. Before, this guy here, this young man, made the stupid assumption that energy comes only in certain packages, quantums. Okay, so basically we can now associate at least such a maximum of such a Planck distribution with temperature of the body. Okay. And then basically we can then associate these wavelengths that we have here with temperatures. And we see microwaves, this corresponds to temperature of Kelvin. What was a Kelvin again? Just in case you haven't heard it. Well, it's unlikely near Glasgow, Kelvin River, Kelvin Grove, where Lord Kelvin basically worked. I think his name was Thompson, and if I'm not wrong, he was from Largs, and later then became professor, this big guy in terms of thermodynamics, was nobled, then adopted the name of the river next to Glasgow Uni, so Lord Kelvin. It's basically the same scale as Celsius scale. Celsius did boiling, freezing point of water, boiling point of water, 0, 100, and then in between 100 scale yards. Fahrenheit, how he did, I have no clue, and I'm European, so I don't care. So Kelvin basically does the same scale, the same division of a scale. It just shifts it to the absolute 0 point. The absolute 0 point where everything is standing still, not even electrons would move or atoms stop moving, everything stops moving. And this is the case by 273.15 Kelvin. Celsius or 0 Kelvin. 1 Kelvin is then 272.15 Kelvin. Very, very cold for us, but already a degree Kelvin. This is basically when you have microwaves, how cold it is. Infrared, we know if you take a photograph of your house, this heat radiation that you get then, this infrared, in the infrared, this is obviously, if you can take it of a human body, it's 37 degrees, or maybe on the surface it's a bit less, 36 degrees, but that's about the dimensions. So obviously we can there again associate the heat of the body with the radiation it emits, which is then infrared. Visible, well, surface of our sun, a couple of thousand degrees Kelvin, or a couple of thousand degrees, it doesn't matter whether you have Kelvin or Celsius, it's the relative error is then at some point so small. Well, X-rays, you would have millions of Kelvin. So we are working obviously very cold in a few Kelvin. So, well, if I say no, was no waving here, that's of course obviously Kelvin, but we see this is a log scale. So I should have waved here with room temperature, so 300 Kelvin. This is about where we usually have our daily experiences. Yet, you see, we can basically associate wavelengths or the center of a Planck distribution with a temperature. Yeah. There were no guys that wanted to do microwave astronomy. More or less, it's just possible, but microwaves, we often have already big problems because often they are absorbed in the atmosphere. There's water, some of the microwaves make the water rotate. So they are gone. A photon interacts with a body and does something, it's usually gone. Of course, it can also go the other way. The water molecule stops and the kinetic energy it's irradiated. So it becomes a photon again, or light particle. So there were now two guys, Penzias and Wilson by name, and they wanted to do this microwave astronomy. Built this, what is called a horn antenna. Here you see these two LEDs, one a bit taller, one a bit smaller. Build the average height of a human, and you get the size of this. It looks a bit like one of these old listening horns that old deaf people used to have before hearing aids became a bit more sophisticated. So these guys built this antenna, do the electronics, look forward to do the measurements. This was in Murray Hill, New Jersey, in the US, at the Bell Labs. Bell, the guy who invented the telephone, made a fortune. And then he took this fortune, made a foundation, and with this foundation, he funds, via the Bell Labs, basic fundamental research, which I think should be the luxury that a society should afford. And not always just ask, what do I get from, what is the next technology that I can exploit and economical benefit? There should be something like this philanthropist. Well, fundamental science should be also be funded. It's a luxury to society, but sometimes you stumble over effects that then can be exploited. Giant magneto-resistance effect, and suddenly you could build data storages factors and factors and factors better. So these two guys basically built this and then switch it on. And what happens? Well, so here you see them again, Ron Wilson and Arno Penzias. What happens? They had a constant noise signal from. And then, is it the electronics? So you take a pulse generator, put it at the very front and go through each step. Wasn't the electronics. Then, of course, if you have such a construction, and well, we change the reference frame. If you are a bird, that looks like a superb nest. Perfect for building your nest in. Okay, well, they removed the nests, but the birds still came. And then they made droppings. And the droppings, well, these guys started cleaning them out. And in order to get the birds away, they even got themselves a hawk. So to scare the other birds off. Didn't help. They still have the signal. So what are you doing? You go to your mates and complain. No, this Murray Hill is not far away from Boston. Boston, Cambridge, Harvard. You have the brilliant theoretical physicists. And some of them, these were a guy called Alpha, another guy called Gamma and Herman. They basically heard about this theory of Big Bang. Everything compressed, super hot energy density, and then expanding universe. So the effect that happened, at some point, there must be a point where atoms can form and light freely propagate. And this should form, according to them, a microwave background, where you have constantly this noise. And sorry, I need now to stop, because there seems to be a delivery from the Amazon man. Sorry about this. So stop sharing. And I will then continue about this noise, and we are back basically that we have now everywhere this microwave background. Well, first of all, before I stop, stupid me, so share back, share. Oh. So you should see now again the slides. So this noise corresponds to microwaves. And if one makes a blank spectra, this was about 2.7 Kelvin. Cold. Very cold compared to what we would expect when the first atoms form, that it's very hot. The explanation is, of course, the universe expands and the energy density drastically drops. And while it is this hot, this radiation that corresponds to thousands of kelvins of visible light, or maybe UV light, the universe expands and you get the redshift. The wavelengths underneath gets longer. You get microwaves. These two guys were not the only one that detected the microwave. If you click, take now a break, or click on this link that is provided in the lecture notes, you will see how every of your grandparents and maybe even parents detected with their TV this microwave background, this constant noise. So this was the time before smartphones, when we just left our caves, and now this guy is here, of course, as usual. My wife orders and I'm distracted. So please have a look, and then next video I show you what, tell you what you have seen. Sorry about this.